I'm going to just make an introduction. For some of you this is boring because you know, for some others maybe this is new. So what we have in astrophysics nowadays is lots of data. It's a huge amount of data coming because we are having bigger and bigger telescopes on Earth, and then we are throwing up all these satellites so we can observe a lot of things and get lots of data. One of these, the catalog of the data that are coming is the data that gives us position of the galaxies. I'm here talking about galaxies. Galaxies are much bigger than stars and other things for which turbulence is important. So for these catalogs, basically galaxies, a single galaxy like our own galaxy, Milky Way, is just a point. So we don't really care what goes inside the galaxy. For us, this is just a point. And these data, basically, here we are sitting right at the center, and we are making a cut through the universe. So we are seeing far and far away. And then this is what we are seeing. This is every single point is a galaxy. Don't worry about the colors, just the galaxies. And we see that the distribution, this is really goes far back into the universe. And the distribution, as you see, is not really homogeneous. So it's like spongy distribution of galaxies on very large scales. This is huge scales. This is like few hundreds of megaparsec. Just for reference, 1 parsec is like 200,000 times the distance between us and the sun. And this is of the 10 to the power of 6 of that. So this is going back in time, and this is going also far into the universe and also back in time, because it's a huge distance, so the light is taking a finite time to get to us. So as we look back, as we go far and far away, we are looking back and back into the time. So this is really a spongy structure the universe has. It's got filamentary structures, and then there are all these clumps, and then there are all these voids that are shown here by dark sort of regions.
Why do you have hours? What are the labels?
This is because it's projection onto our sky. So the sky around us.
Rotation time?
No, it's not. Has nothing to do with the rotation, because when you have got when you project onto the sky, you can just see as just 12 hours and then 6 hours, like just astronomical. It's just directions.
Angle measurement.
Exactly. So it's astronomers. There's no rotation here. It's just yeah, that's right. It's just astronomers' way of projecting everything onto our sky. So it's angle. So but what is important in this direction? This is the distance, right? It's going way away from us.
So if I sort of put the Big Bang, it would be in Paris on this picture, or where?
Big Bang is for you. Big Bang is not really here. It's very near us, right? So. We are not going back to Big Bang yet.
Yeah,
it's far off. I'll show you. But this is basically, okay, it's a far away, it's a very large distance, but still in the scale of Big Bang and the universe is pretty small, right? And so we can go even farther back, so right back to as far as we could see, because we could not see Big Bang, even if it was the light from Big Bang would really not be able to reach us. The universe is not transparent. So when we go really far back, we also have data, very good data, and that's CMB data, cosmic microwave background data, and that also tells us about the distribution of mass. Another thing that I should say here, these galaxies are just the matter that we see. They're luminous, they just emit light. But what we believe is that this is just a very little part of the mass that exists in the universe. These galaxies, for you, are like, in some sense, they're like passive scalars. They're just tracing the mass distribution of an underlying fluid, the dark matter fluid. So there is a fluid which these galaxies are tracing, and that fluid we do not see. Right? So we use these galaxies to infer information about the distribution of the underlying unobserved dark fluid.
How you know that they're tracing it? How you know how they interact with it?
Yes.
Just gravity?
There's only gravity, yes. And there are lots of observational evidence that there is such a fluid. From basically, one of the reasons why this reconstruction is important is because it gives us another evidence for the existence of this underlying fluid. From the motion of these galaxies, we can infer information about that underlying fluid. That's why the velocity of these galaxies are important. But these data, the astronomical data, they do not give us the velocities of these galaxies. They're just giving us their positions. The aim of this reconstruction work was starting from the position of these galaxies. We wanted to find out what their velocities were. Because the velocities are the important quantities that give us information about the distribution of mass, not the positions. The positions, okay, informations, but they're not that interesting. The velocity of these galaxies are very difficult to measure. That's why there are very few observations. It's not easy to measure these velocities. It's extremely hard. You have the position of millions and millions of the galaxies, but for the velocity measurements, we only have measured the velocity of a few thousand galaxies. So it's very difficult to measure. That's why you need modeling, like the reconstruction modeling, to get the velocities. Now this very patchy universe, which is very homogeneous, looked pretty homogeneous far back in time, when we went back to Big Bang. It looked almost like a black body, completely homogeneous, thermalized, and it was emitting at 3 Kelvin. And this 3 Kelvin is pretty constant. There is, however, it can, however, not be completely homogeneous, because if it was completely homogeneous, we would not be able to form structures. Because the structures that we observe today, galaxies, the phenomena, the worlds that observe, they are actually the growth of these small fluctuations under self-gravity. So there must have been little fluctuations, and these little fluctuations far back in time, this is almost the time of Big Bang, have also been measured very accurately, and they are very tiny. They are like 10 to the power of minus 5. So that temperature that we measure of 3 Kelvin, which is everywhere, is a fluctuation on it of 10 to the power of minus 5. And these little fluctuations are the reason why we actually exist, or the reason why there is universe, there is galaxy, there are galaxies, and there are all these structures. So I'm just going to, because it's 9 o'clock in the morning, so I'm going to show a little food. Sorry?
Root mean square of the fluctuation?
Root mean square. Yeah, this is, yeah, that's right. But it's,
Are the fluctuations Gaussian or not?
that's what we think, yeah. We think they're Gaussian.
Okay.
And if they were not Gaussian, so this is one of the questions actually, are they Gaussian? They're to good approximation, they're Gaussian, but they could be very small deviation from Gaussianity, and that is very important to measure. With the present measurements, we cannot really put bound on that little deviation from Gaussianity. That is important because that's a good test of the theories, like inflation theories and so on, of the formation of the structures initially. But with like this Planck, which is a satellite which went up and soon has going to have data, we can put bound on that non-Gaussianity. So I'm going to show you.
What about polarization?
Yes.
Because you know everything, then we can ask you.
No, yeah, polarization, no, we have very little information. And this Planck, we are not. So polarization is very important also. But these measurements tell you very little. And then polarization is very difficult because there are lots of contamination from polarization coming from other objects, intermediate objects. So this Planck, again, the polarization would be improved, but then there are lots of other experiments who are actually going to focus really just on polarization, which are actually quite important. So this is, I'm going to show you a little thing to show how we go from this present patchy structure far back in time. And this just to amuse you at 9 o'clock in the morning to wake you up. So this is where we are, right at the center. These are all the galaxies around us. So we are going far and far and far back. As we look far and far, we go early in time. And finally, we reach basically to the limit that we can observe. And these are just the tiny initial fluctuations that are coming from the cosmic quantum background. This is basically the initial black body at which the universe was radiating at 3 Kelvin. So how do we model this actually? This is basically all we have. Initially very uniform and now sort of highly structured. So just to say something, comparing to what you are doing, there is basically no, on large scale, there is basically no Navier-Stokes turbulence here. The cosmic fluid from this observation is collisionless, so there is no dissipation here. And it's only forced by gravity, and it is compressible. So you see there is no vorticity, there are none of these interesting things, physics going on here. On large scale, in some sense, universe is pretty boring. There's no electricity, no magnetic field. So, but then it's in some sense, it's good because we can do nice analytic works. Now, how do we model that? Well, there are many ways of going about this, but I just prefer this way because it's more pedagogical. So we can start by just writing for this underlying mass distribution, which is collisionless, and interact only to gravity by Klimantovich density, just Dirac delta functions. And then you can show that if you ensemble average that and assume that this is collisionless, which the observations are telling us that this underlying dark matter fluid is collisionless, you arrive at Vlasov-Poisson equation or collisionless Boltzmann equation. So there is no collision term here. And you can go about to solve this equation. If you are very ambitious, you want to actually, the best way is to really sit down and write code and solve this equation. Nobody has done that. This is really very difficult to do, because you have to solve this partial differential equation directly in 6 n-dimensional space. Has not been done. All that has been done is in 1 dimension, and I think maybe some people in 2 dimensions. You have done something
Only one.
in 1
A
dimension.
long time ago.
Yeah. So people are trying, but nothing yet. Another way that you can solve this equation is what we're all familiar with, that instead of going and directly solving it, you can solve the characteristics, basically the equation for motion, dr, dt, dd by dt, Newton's equation, and then this is what people do when they run n-body simulations. So they have initial condition, then they run their simulation by solving these equations of characteristics, and that's n-body simulation. It's pretty successful, n-body simulations. Tells us a lot of things. It's difficult because there are many little structures that you miss. There are lots of numerical problems. And in some sense, when you look at the universe on large scale, you don't really need them. You can do lots of analytic works because you are in sort of linear, semi-linear regime, and analytic methods are very capable of telling us, giving us a lot of information. So this is a simulation, but n-body simulation that people do start from completely homogeneous initial condition. These fluctuations grow under self-gravity. Basically, you see that you form these clumps, filaments, voids, and so on. And it's a good representation of what the initial observation is that we have the first slide that I showed.
So typically, how many particles in this simulation?
Now, they are actually, initially they started very, very few, but now they can go to 1 billion. They are really a state-of-art simulation where go to 1 billion. So, and this is, when they do large-scale simulation, they can go to billions, but then, they can zoom at individual structures, and then they can put sort of billion on those structures. So they can, it's a hierarchy of zooming, so you have basically multi-scale simulations that can
So it's
have good resolution on lots of scales.
just Newton's problem, no
Just
dissipation, nothing?
So this is just for that underlying dark matter, which is basically most of the mass in the universe. These little particles, galaxies, they're very little. They're like a few percent of the whole mass that is in the universe. So these are the simulations, but as I said, we could do analytic work, and this is what most of you are familiar with. We can just take the moments of these equations, and then we have fluid equations, right? But we don't have Navier-Stokes equation because we don't have any collision term here. And so what we have is basically Euler equation, but we also have gravity here. This is what some of you work on Euler turbulence, we don't have gravity, but here we have gravity. This is the velocity field. Sorry, these notations are not, this is really sort of redefined time, but I'm just putting time here. And these are the velocities. And this is the velocity, and this is the gradient of the gravitational potential. This is the continuity and Poisson equation, of course, you have here, which you don't have in turbulence. Now, what happens is that when we linearize this equation, we can linearize these things and solve it. Basically, when you go far back in time, as time goes to 0, another way is to see that if time goes to 0, this will blow up. So in order for this not to blow up, V has to be minus the gradient of gravitational potential. Another way of looking at this is that you linearize it, and you see that V is equal to minus the gradient of gravitational potential at early times. Basically, early times also means linear regime, where the structures were not so direct. And this is very well known in cosmology. It's one of the people who actually made huge contribution also to turbulence. So Zeldovich approximation, because it was really originally proposed by Zeldovich. So if I take Zeldovich approximation, basically it's telling me that Lagrangian derivatives of velocity is 0. That means the particles have inertial motion. Particles basically move with the initial velocities all along the trajectory of the particle. The velocity is conserved. And so I can just write it like this, just a simple inertial motion. And then if I plug this thing in the equation of conservation of mass, so I have a little element of mass initially, that these are Lagrangian coordinates, go to finally Eulerian coordinates, you see that I can have this equation, basically. Now this is really what Zeldovich first wrote, and you see that this determinant 3 eigenvalues, if one of these eigenvalues are much bigger than the other 2, there's going to be a gravitational collapse along one direction, so you're going to form pancakes, Zeldovich pancakes, collapse along 2 axes, so 2 of these are bigger than the other, would form filaments, Zeldovich filaments, and all of the 3 would form clumps. And this is really what we observe on large scale. So from this very simple formulation, Zeldovich actually long ago in 1970s predicted the distribution of mass in the universe. And this is what you do when you do a Zeldovich simulation, this Zeldovich approximation in 2D. You see the formation of these filamentary structures that we actually observe. The galaxies do have these filamentary structures. They do form these clumps, and there are these void regions where there's very little mass. This is comparison of Zeldovich approximation with full simulation. Okay, if just statistically on large scale, you see that similar structures arise in most.
I mean, is there a better characterization of this equivalence than just pictures? Are there correlation functions?
Yeah, people have done lots of statistics, sure. There have been lots of, so I'm not going to go through the details of, there have been lots of statistical analyses of comparing the two, and it stands pretty well. As long as you stay away from these multi-stream regions. These are the regions where Zeldovich approximation basically collapses. As you see here, these filaments are much thinner in real simulation than in Zeldovich approximation. And the reason for that is that when fluid elements come together in Zeldovich approximation, there is nothing to stop them. There is no viscosity, there is nothing, so they just go through each other. So the multi-stream regions, they just grow in time, whereas in real simulations, the multi-stream regions do not grow. So the statistical analysis has been very
when you speak about full dynamical equations, it is an n-body simulation, or it is really an evolution of the fluid dynamics expression?
No, this is n-body simulation. Yeah.
Well, in principle, it should be rather
some expansion.
Yeah.
Exactly. So there is all in these equations. Actually, this time is really rewritten such that the expansion of the universe is taken into account. So it really has. So when you think about Zeldovich approximation, you think about particles moving, having inertial motion. It's not really true that there is no gravity. They have inertial motion because the effect of gravity is there, but then there is this counterbalanced by the expansion of the universe. So you're not really throwing away the gravity. It's just the property of an expanding universe. And so this is what happens. Real simulation would have these, in the phase space, you would have all of these singularities, caustics. In the Zeldovich approximation, you form one caustic, and then this is where the velocity is not defined. These are the multi-value regions that grow in time. Now, what people have done actually, Zeldovich himself at the end of his life did with Shandarin, was to say, okay, this is the area where Zeldovich approximation failed because there is no viscosity, so I introduce a sort of an artificial viscosity. And that's when he actually proposed the Berger's equation, on which Uriel worked a lot. And so there's an artificial viscosity that you put in these simulations to stop these filamentary structures sort of expand in time. And that somehow is, when you do the statistical analysis, is a better representation of this than the Zeldovich approximation. And you see that the difference is that here in the Zeldovich approximation, you are forming all these caustics, whereas when you put the Berger equation with this sort of artificial viscosity, you form shocks. Now, one of the things that we wanted with Uriel a long time ago, we've never done that, to find out is whether there was any origin for this viscosity, whether there was any physical mechanism in a self-gravitating system that would give rise to this viscosity. Nobody knows, but we know that it works.
Yeah, but there is one also cause of confusion for people who are hydrodynamicists, because you know, of course, that in the real world of nonlinear acoustics, etc., there is no multi-valued velocities and things like that, because there are shocks appearing. Whereas out there in the universe, where the particles have basically no interaction, the mean free path is roughly infinite. Multi-streaming, of course, does exist. It's just not the multi-streaming predicted by the Burger's equation. It is a poor approximation.
That's right.
But the total suppression of multi-streaming that would result from using the so-called adhesion model, which is the Burger's equation in the zero viscosity, is also very wrong.
Yeah, sure. So these regions actually we do see them, see like this here. We want to cross a model them. But as in Becker's equation, we are replacing them by shocks. Now, okay, so let's go back. This was just like a little diversion just to tell you about the Lewis approximation. So this was just Lagrangian derivative of velocity 0. And so this was our inertial trajectory. And this velocity, of course, as I said, as we found from the linear theory, can be represented by the potential, by the derivative of a potential, gradient of a potential. And then you can rewrite this like this, and you see that basically the Eulerian position x is the Lagrangian derivative of a potential, which is a function of the Lagrangian coordinate q. Now, if the final position is the Lagrangian derivative of a potential, then you can do a Legendre transform and just inverse these coordinates. So you can write that the Lagrangian coordinate is a Eulerian derivative on another potential, yet another potential. And this is yet another potential that we are looking for. And if you go further, you see that this is the inverse Lagrangian map. You use the Legendre transform. And now I do the same game as the Lewis plate, put this back in mass conservation, and I somehow rewrite the Lewis equation using this Lagrangian map. And this gives you a nonlinear equation. It's called Monge-Ampère equation. If you look sort of closely, it looks like Poisson equation. It's sort of nonlinear. You have the potential here, second derivative, and then you have the density field there. Now this initial density is more or less constant. Now how do we solve this? This equation goes back long in time. For a long time there was no solution to this. And finally Yann Brunier made the analogy between this problem, the problem of Monge-Ampère equation, basically the elliptic Monge-Ampère equation, and the problem of mass transportation. And he found the variational solution to our equation, to the Monge-Ampère equation. Basically, the solution to Monge-Ampère equation is given by the minimization of this quadratic cost function. Now, there is no pedagogic way of going from Monge-Ampère equation to this variational approach, which is normal for you, but when I talk to astrophysicists and cosmologists, they get very confused. But anyway, this is the variational solution to the Monge-Ampère equation, and if you just go ahead and discretize this, you can write this as a quadratic cost function. Basically, the problem, the cosmological problem of reconstruction is reduced to the problem of assignment, thanks to Brenier. And this is basically telling you that for given position, present position, Eulerian position x, you have to search and find the Lagrangian position that would minimize the quadratic cost function. And this computationally can be very difficult to do. Actually, if you were just to do this by brute force, it would have a complexity of n factorials, as you can see. Our algorithm, however, worst case is n cubed. We found the algorithm which was originally written by somebody.
That's not worst case. That is the best proof.
Best proof, okay.
Yeah,
And the
well,
one that,
in a sense, it's the worst case. Yeah, we do hope it is not as bad as that. But
yeah.
that's the only case. There's a reproof that it cannot be more than n cubed.
Yeah. And then the algorithm that we found has a complexity of n to the power of 2.25. And Yann Brenier has a conjecture he hasn't shown is that actually you can solve it with a complexity of n log n. There are also people who actually tackled this equation directly. I think Olga, Vlad, and Uriel, they just have been trying, if I'm not wrong, to actually solve this directly, because you can also solve this directly.
What is astrophysics or cosmological sense to the left-hand cost function?
this is, yeah, actually it was my next thing, and I wanted to skip it because I'm running out of time. So why is this just the quadratic cost function? Where is this coming from? Why is it that this problem, there was gravity and there were galaxies and so on, you just a simple cost function? If you look carefully at this is just like the action, or the Lagrange action for particle with initial, just a kinetic term, right? There is a factor of time, but it's just a kinetic term. So this is basically a full action going from the initial uniform universe to this final inhomogeneously distributed universe. And we see that this action has a kinetic term, and this term coming from, because there is expansion of the universe, and these are the potential terms. So if I just were to ignore these terms, I would just be having this kinetic term. And that's really why there is this quadratic constant. This is the physics of this quadratic constant. I'm not going to go to the details of these things. Now we've done this reconstruction actually with Uriel and with Michel Renaud, and we managed to actually do reconstruction in spite of this complexity of these codes on 2 million particles, 128 cube. And this is now the initial Lagrangian coordinate that come out of this formalism, basically Lagrangian coordinate that comes out of this formalism, plotted scatter plot against the simulated Lagrangian coordinate. See a pretty good straight line with some scatter. Of course, the reconstruction is not going to be 100%. It's not going to work 100% because the reconstruction was based on the fact that we don't have multi-streaming. Basically, the potential is convex, and that there is a potential flow. And these two hypotheses can get violated, right? Then you go to highly nonlinear regime. So, and that's why there is a scatter. We don't expect there to be just a perfect line. These are the velocity fields, so on very large scales. This is the simulated velocity field, basically coming from simulation, and this is the one that we have modeled from our modeling, and you see that they agree with that. This is displacement field, don't have much time now. We can also apply this to real data, and this is where we are. We are sitting here, Milky Way, and this is our universe nearby. And we have the position of these galaxies. As I was telling you, this big catalog give us the position of these galaxies. Using the positions, now this is actually quite amazing that we only have the position of the galaxies, basically the radial positions, right? And from that, we find the 3 components of their velocities using the reconstruction. And these are the reconstructed velocities. You see that what's happening in our local universe is that you don't really see any sort of vorticity or complications like that. You see there is a flow. And this is a huge concentration of mass here. It's a Virgo cluster. This is another huge concentration of mass. Some of you might have heard of. It's the Great Attractor. And you see that the whole of this region, this huge region, is moving into that direction. This is what we expect. So what do we do with these velocity fields? Now it's good we have got these velocities. That's what we were looking for. But what's the use of these? Velocities are actually quite important, first of all, because they tell us about the mass distribution, how much mass there is. If there's more mass here, even if I don't see it, if you put a galaxy here and it's going with a large motion, if you measure its velocity, it can tell us what is the mass, because it's just gravity. So the velocities can tell us about mass. And this is a problem of missing mass, so this is like a cluster. We take a cluster, this is cluster of galaxies, contains a lot of galaxies, and then we reconstruct the velocities of these galaxies, right? This is one of the clusters, and I'm reconstructing their velocities. So we are sitting here, and this is the cluster, and these are galaxies that are falling into these clusters. We can't observe the velocities. We use our reconstruction to find their velocities, and then using their velocities, we can find out how much mass there is. If there was no such a huge concentration of mass, I would expect all the galaxies to be moving on this straight line, basically Hubble flow, the universe on expansion. But because you put a huge concentration of mass, there is fluctuation around this straight line Hubble flow. And the amplitude of this fluctuation tells you about the amount of mass that you have in that cluster. So from the velocities, we can actually find out how much mass there is in these clusters. It's a huge amount of mass. It's not at all explained by the amount of the luminous matter, the light that you see. So there must be a lot of hidden mass. Another application of this, which is a very recent work that we have done, because I'm hoping that you're also interested in the application, it's not just a nice mathematical formulation, is basically the foundation of cosmology, and that's the cosmological principle, that we assume that on large scale the universe is actually homogeneous and isotropic. Now this was challenged many years ago by people who were claiming it's fractal and so on, and we know that fractal formalism can explain homogeneity, but we don't think that the universe is really fractal. But is the universe really on large scale homogeneous and isotropic? Because the local universe is not homogeneous and isotropic. As you saw, there are voids, there are filaments, there are clusters. So locally, we are not in a homogeneous and isotropic universe. But as we go far and far away, we are hoping that the universe will become homogeneous. Because as you saw initially, with that cosmic Marvel background, the universe was pretty homogeneous. Now the question is where? Where is the boundary? At what scale we reach homogeneity and isotropy? And this is one of the questions, fundamental questions that we can answer from the velocity field that we have reconstructed. And so what we have done is that basically we have looked at this observation. This is the first map of the universe. This basically is telling us when this is a temperature, so these are hotter regions, colder regions. Basically these are red shifted, these are blue shifted, which means that this is a Doppler shift, which basically means that we are sitting right at the center. We are actually moving, going away from this region and moving towards this region, right? So if we have got this huge motion that is producing this dipole, and if we are only moving through gravity, that means that there must be huge structures that are pulling us. If there are huge structures that are giving us this direction, that means that the universe cannot be isotropic, because we have a motion in a certain direction. If everything was isotropic and homogeneous, we would not be moving, we would not be having a preferred direction of the motion. So using our velocity field, we can find out what the structures lie here, and how much mass they are, and whether we have reached homogeneity and isotropy. So what we have done is that we have taken one of these catalogs, and we have done our reconstruction of Monge-Ampere reconstruction on bigger and bigger and bigger sphere around us. And at some point, we were hoping that we were going over this field. Basically, we have reached homogeneity and isotropy. And so this is what we have done. This is what we should reach if the universe was homogeneous and isotropic. And we expect to reach this soon, if not too late, because we have a standard model in cosmology that tells us that universe is homogeneous isotropic, and this homogeneity and isotropy is reached at few hundred megaparsecs. So this is what we do. We are getting our first sphere, and we are reconstructing velocity there, and this is the bulk flow, if you like. This is the bulk flow that we are measuring in that sphere. Then we take a larger sphere, we add more structures. It's a bigger sphere, as you see here, and then we are finding the velocity in that. So it's increasing, but it's not reaching there yet, and we are already at about 50 megaparsec, and we expect to have reached homogeneity. We are taking then another bigger sphere, and we are doing reconstruction there again, finding the bulk flow, and then we are here. We are not reaching there. And then at the end of the day, if you go very far, we don't reach there. This is as far as we can go, because we don't have observations that tell us the positions beyond that. And we haven't reached this line. This line is basically a standard as a measure of the homogeneity and isotropy. We should have reached this line.
Sorry, I didn't get how you predicted this velocity.
From our Monge-Ampere catalogue.
No, the observed local brute velocity. The one that
this is coming from the microwave background radiation. That's observed. So this is this one. This is this dipole. This is what we observe. When you look at the temperature and isotropy, the very first map you have is not those little fluctuations. The very first map you have is this. It's a dipole. So this is an interpretation of this. Actually, we can have one interpretation. An interpretation of this is that we are moving in a certain direction. And to have this temperature, this huge dipole, we should be moving with this velocity.
Why do you say an interpretation? What else could it be? I mean, if you move in a black body, you see a dipole.
Yeah, that's right. But then, if you move in a black body, you see a dipole, yes. But how do we know that we are moving with this? It could just be that the universe has a strange geometry. So one of the people like Paczynski, when this came about 25 years ago, has proposed that actually this is not really, well, maybe a small part of it is due to our motion, but the universe really itself has a strange geometry. It's not completely spheric. It's like in the elliptical universe, you can generate such dipoles. So it could have more fundamental cosmological implications. And as you see, we do not recover completely that. So that does really mean that there is a problem for homogeneity and isotropy, the cosmological principle. At least we do not know where. And from the present observation, we do not know where we cross the limit, where we can actually say safely that we have reached to homogeneity and isotropy.
Well, are you saying that you have predicted now that there really is a temperature fluctuation on the scale of the horizon when the microwave background formed? Because you don't get up to this line 627 kilometers per second.
That's right, we don't get that. Yeah, exactly.
You get sort of three
Yeah,
quarters
we get
of the
about,
way.
exactly, we are with about 75%. We are with, and the direction, this was the direction, okay, but this is a detail. And the direction wise also, because that's what I was showing you was just the magnitude of this velocity. And the direction wise, if it was really homogeneous isotope, we should be sitting here, right here, or around this 1 sigma, but we are sitting here, so we are about 20 degrees away from that. So from this, see, the reconstruction formalism is not useless, it can really be useful. Now these are the models actually, and this is another thing that we've done recently with Jacques and other collaborators. So this is the data again. This is the bulk velocity as you take large and large and larger sphere. You see this is redshift, maybe you're not familiar, this is distance. So you go to take a large and larger sphere and you find what is the bulk motion of this sphere. And at some point, if the universe is homogeneous and isotropic, this bulk motion should be zero, or near zero, without fluctuation. The model, actually, the isotropic model is saying that as you go far and far away, you should be reaching these, basically. So you are going to about 50 kilometers per second. But this is the data. And the data is not showing that. So maybe it's sure that on a very large scale, the universe is homogeneous isotropic. We are almost sure about that because we have the cosmic microwave background radiation, which is a black body. But we don't know at what point we are getting there. For the time being, we don't know because we don't have good data. And for the time being, the models that assume that, we are reaching this isotropy and homogeneity earlier than later, these models are not really, they are not working. Now I just want to finish actually in 5 minutes. So let me just summarize. We had this problem, Monge had this problem of mass transportation. This is actually a sort of drawing that was done by Uriel himself. And he was brave enough to put this in our paper. So Monge basically, and actually Uriel knows the history and it would be very interesting to hear about this. He was working for military, he was working on a military program many, many years ago, hundreds of years ago, and he wanted to know how to optimally transport these
Please don't show this to the Hamas.
I'm sure you've already showed that. So how you would do that, transport optimally mass, sort of basically piles of mass, to holes or digs in the ground. And this was the Monge problem. He wanted to minimize the cost for the military or whatever, we don't know that. And then Ampere came and he formulated that. He formulated the Monge-Ampere equation on which we have worked, and Kantorowicz at the same time related this Monge problem, the problem of Monge, to problem in linear programming, and he made a lot of use on that in economics and I think also in biology.
Yeah, they celebrated the 100th in the next year.
Oh, that's funny. We are doing earlier, so Uriel came, we are celebrating 70th. And so there it is, we have got the cosmological problem, and
I suppose this is a reconstructed picture.
I couldn't find a better one on the internet.
Okay.
So you don't agree with Petroneo and company about fractality?
Yeah, that's right.
You do not agree?
Well, I worked actually on Petronero, so I think so fractal analysis is a way of actually looking at the correlation function of galaxies, and it does a very good job. But I think Pietro Nero went a bit far to say that the universe is fractal all the way, because you cannot, you will have a big problem to say that universe is fractal, because then you will have a problem with that 3K black body.
It's fractal as long as it can see.
Yeah, that's bad. As long as you can see, you don't.
And it's also as long as you can see.
But
It's not ad hominem, right? This is data.
But
Black body.
I wouldn't. Yeah, I wouldn't say as far as we can see. It's disputed. So even this that they are showing that because there was a dispute with people, you have a dispute with people that, for example, when you go to about 100 megaparsec, which is very far, you would reach. Some people would say you would reach homogeneity. You would say no, it's not homogeneous. It's a
What does the data say?
But the data is not so. It's not conclusive yet. So we really need better data.
I mean, we had this problem already many years ago with data, because together with Jean-Pierre Ekman, we proved that if you have a set there of galaxies, then the visible set doesn't have the same dimension as the whole set. And the theorem is that if the dimension of the set is larger than 2, you're going to see 2. And if the dimension is smaller than 2, D, then you're going to see D. And this is how we interpreted why they always see 2 dimensions.
Yeah.
You can see more. Because if there's more, then there's going to be an obfuscation.
Yeah.
So I was always having a problem with the data analysis, but I'm still convinced that what they see is a dimension 2, and people have to realize this. I mean, and it's I think very careful analysis cannot be just thrown aside. Huh?
Yeah, you need very good analysis, and you need very good data. So the data already, when it comes to us, it's already sort of.
That could be checked on
Yes, you may.
Last question.
Okay, so about your missing quarter in temperature, shouldn't the fluctuations of temperature and mass and velocity at this time when the black body radiation formed, they all come from a growing mode, so these fluctuations should be correlated. So shouldn't there be some consequences of you missing 1/4 in temperature fluctuation? Saying the initial velocity somehow would mix up everything.
Well, the problem is the initial velocity we don't know. So all we have initially is that temperature fluctuation. So it's, even locally it's very hard to measure velocity, if I understand your question correctly.
Well, I didn't formulate it very well.
Well, a very short remark.
There is just one comment on the work that Vlad, Olga, Barbara Bilon, and I have done in recent times. It is that we now understand why this method of reconstruction actually works much better than one would have predicted on the basis of the validity, of the limited validity of the Zadovich-Oberles approximation. Is that the theorem of Bonnier that you referred to just assumes that we water it down, that the velocity is potential not just in the Lyrian coordinate but also in Lagrangian coordinate, which is true within the Zadovich-Oberles approximation. But there is a higher order approximation which is called the second order Lagrangian approximation, which has been developed after the Zadovich, mostly by French people, by the way. Which also to the next order gives a velocity which has this potential character in Lagrangian coordinates, and which is also then reconstructed exactly with this procedure. So actually the reconstruction is a better quality than one would have expected.
Yeah, sure.
Okay, yeah, thanks for that.